So I have started recording. So welcome all of you. So this is the seventh session. So this is seventh session. We will solve some problem in this session based on the topics which are covered by the professor in the week seven. And first, I will introduce myself. This is Vijay Ran. I'm a Prime Minister Research Fellow in IIT Delhi. And today here we are going to solve the problem based on the one and two dimensional NMR spectroscopy for the chemist. Right. So before going to the problems, does anyone have any problems uh, regarding the topics which are covered here? So you can ask me now, or at the end of the session also you can ask. So anyone have any doubt here? If not, I would just like to show some NMR spectra here. So in this week seven, we have almost covered all the topics in the 1H NMR spectroscopy, and we are slowly moving to the 13C NMR spectroscopy. So I will just show you one NMR spectra, 1H NMR spectra, how it looks like. So this is the I have opened the spectra in the YumNova software, which is like generally people's traditional use for the processing the NMR data. And if we took the any file NMR file, so in initially the file will look like in the FID format. And if you open the file, yeah, the file. So this is the carbon data, right? I will check any 1H NMR file. Yeah, so this is how the 1H NMR spectra looks like. So which has the, if you look at here, at zero, this speak is referred to the EMS speak. So we generally put this as a standard, which we generally add in the proton NMR spectra, 13C NMR spectra, as well as silicon NMR spectra, or we calibrate the our spectra with respect to this TMS peak. So I just calibrated this as a TMS. And can you tell, Ankit, am I audible as well as the screen is visible, right?
Yes, sir.
Yeah, all right. So this is how we generally calibrate our NMR spectra, and we have just referred this the peak at zero as a TMS spectra, and this is the remaining spectra of the compound here. So if you look at here admit region, there are the number of peaks you can see here. Also, there are some peaks in the aliphatic region as well. So this sharp singlet at the nearly 3.2 is generally because of this methyl group in the compound, methoxy group in the compound. So I will show one spectra for which the structure I know the structure. So first I will draw the structure here. So the structure of the compound is like this, which has the one benzene ring followed by five ring containing the nitrogen and sulfur, and which then further attached to the another phenyl ring. And if you look at this one, this compound is like OH here, and here there is one bromine is attached. So how many peaks you are expecting for this compound? So it has the, I will just label these hydrogens. So this hydrogen one, two, three, four. Also in this ring also there are one hydrogen, here one hydrogen and another one hydrogen. Also this OH is also there. So one, two, three, four, six, five, six, and seven, right? And eight. So there are eight protons are present in the in this compound. And also, if you look at the NMR spectra closely, so I have just first did the calibrated this NMR spectra with respect to the this TMS peak at the zero, and then the peak at 1.5 generally comes due to the water present in this solvent. So I have taken this NMR spectra in the CDCl3, So if you look at the 7.26, there will be a peak due to the CDCl3. If you look at this one, so can you see here at the 7.26? So this peak is due to the CDCl3. I will just label it as a sorry, CHCl3 in the CDCl3, the impurity of chloroform present in the CDCl3. So some of the protons in the this CDCl3 is not getting replaced. So that show the peak in the 1H NMR when you take the NMR in the CDCl3. So that's why this peak will here. So this is peak due to the CDCl3 and remaining peaks are here. Also, if you look at the here, the par in the range about 12.5 ppm. So this peak at here. So this peak is due to the OH proton. So if you look at this proton in the structure, I will just show the structure. This proton we can also draw in the form of in this form. So here it is in the proximity there is nitrogen present. This nitrogen, right? So what happened if you look at this green proton? So this green proton and this hydrogen nitrogen, they forms the hydrogen bonding, and because of this hydrogen bonding, this proton is getting much more de-shielded compared to what we are expecting generally for the phenolic protons, right? So that's why this proton is around at 12 to 13 delta values or 12 to 13 ppm. We observe these protons. So if you look at the NMR spectra, this proton is due to the OH hydroxy, sorry, phenolic OH group. And also in the aromatic region, there should be the 8 protons, right? 8 or 7 protons. So there should be 7 protons in the aromatic region. So if you look at the aromatic region, I will just zoom this region. So this is the one. These two peaks are getting merged together. So this is 1, 2, 3. This is 4, 5, 6, and 7. So there are 7 aromatic protons which are here. And also if you look at the multiplicity of these protons, so what are the distinct peaks here? So if you look at the H5, so I will just highlight with the another color here, this H5. So there is one singlet, right? Singlet, or what you can say, there will be a doublet with very less J value, right? Because of this meta coupling here. So we can look into the NMR spectra whether this type of any signal is there in the NMR spectra or not. So I will just zoom the aromatic region. So if you look at here, so the signal at 7.8. So this is like a singlet. If we zoom out, so this looks like a singlet, but in actual, this is a doublet due to the meta coupling, right? So there is, if you look at the J value is less than the. So this spectra is recorded on the 500 megahertz NMR instrument, and the J value for this one is about 2 ppm. So right now I have just not taken long multiple digit. I have taken up to only the 2 digit 7.79, and this another signal also you can look at here. So it also shows the 7.79. But if you look at the spectra, the further value up to the 3 to 4 digit, then we can see the difference in this signal. So this doublet is due to the proton here shown in the circle. This proton. Also there will be a another doublet, right? For this proton, this one, and also another 2 doublet, 4 doublet as well as 2 triplet. So you can look at here. So 1, 2 doublet here. This is third doublet, and if you look at here, there is one doublet is merged with the one triplet. So and there are triplet here. So one triplet and the triplet which merged with the doublet. So there are two triplet present in the molecules because of these 2 protons. So this is how the 1H NMR spectra looks like in reality. So this is 1H NMR spectra of this compound. So if you look at some the 13C for the same compound, so this is how the 13C NMR spectra looks like. So there are one proton due to the TMS here, so small signal due to TMS. And if you look at the aromatic region, there are the signal due to the carbons. But here this 13C spectra we have taken as a proton decoupled 13C spectra. So you have to keep in mind, generally we take the 13C spectra as a proton decoupled. So the proton coupling due to the proton is get cancelled in this type of carbon NMR spectra. So this is like a proton decoupled carbon NMR spectra. All right, we'll move to our problems here. So hope you have got some flavor of the how the NMR spectra looks like. So one first question here is the as I already answered this question, the TMS, that is
Yes.
tetramethylsilane. Yeah, yes, yes, please.
Sir, why the peak of CHCl3 is splitting into triplet?
Question is why? Can you repeat the question? I'll just increase the volume.
Why CDCl3 peak is splitting into triplet?
All right, all right. Why CDCl3 is split into the triplet in the carbon NMR spectra, right?
Yes,
Right.
sir.
So I have we have so seen this. This is the proton spectra, and if you look at the proton spectra, the signal due to the here you can see here this signal is due to the CHCl3, not due to CDCl3 because of the CHCl3 impurity. But if you look at the carbon spectra, this is the carbon spectra, and if you look at here, this is the small signal due to the tetramethylsilane, which is an impurity present in the molecule, right? And again, if you look at this signal at between the 76 to 70 76 to 77, this is the triplet, and this triplet is due to the you are right, CDCl3. But if you look at the structure of CDCl3, so as I have already one mentioned, we take the carbon spectra. First point, we take 13C spectra as a proton decoupled, right? But we haven't decoupled deuterium, right? Deuterium, uh, right? The we call label it as a two. Deuterium is isotope of hydrogen, right? And we use the solvent as a CDCl3. So in the 1H NMR spectra, we observe the peak at 7.26 due to CHCl3 impurity present in the CDCl3, right? And if you take the carbon NMR, carbon C13 NMR spectra, we take as a proton decoupled spectra. So in the proton decoupled spectra, we do the decoupling due to the 1H, not due to the deuterium. So in the what solvent we have in the spectra for the 13C? At the time we have the solvent CDCl3, right? So because of this deuterium, it has the I value is equal to 1, right? And we have the formula. I will just insert one new slides. We have the formula 2Ni plus 1. This is the formula, right? So if you look at here, 2 multiplied by n is equal to 1, and I is 1 plus 1, right? Uh, did I did any mistake here in the writing formula? 2Ni plus 1, I think. So I here is 1 plus 1, it is 2. N is here 1. I think what is the formula for the signal? 2Ni plus 1, but where is the bracket located? The I value for deuterium is 1. So if you put the value of this one as like in the 1H NMR, we put the value of n is equal to the number of coupling hydrogens, right? And I is equal to the spin value for the proton is 1 by 2. So at that time we put the value 1 by 2, and then we get the signal is about, let's say you have the this group. So at that time we put the value of this n is equal to 2, right? 2n. N is, I think, here. Sorry. I is 1 by 2 plus 1. So this will be like this get cancelled, and that time it will get the we get the three protons here in the three signal when we have the two hydrogen. That time though we get the three signals. In the similar manner, when we have the I value at that when we have the I value 1, at that time we get the for one coupling deuterium, we get the triplet. So I will just check the what is the actual formula for this one. Are you able to see the screen now? Right. So we have the formula 2 Ni plus 1. So here in the 1H we take here. So let's take example of the CHCl3 only. So CHCl3 and CdCl3. So in 1H NMR, so for proton, the I value is equal to the 1 by 2. For deuterium, I value is equal to 1. So in the example of this CdCl3, when you take the 13C NMR spectra, so this carbon is coupled with this carbon coupled with the deuterium, right? So we have the 2 multiplied by N is equal to 1 multiplied by I for this one is the I value of deuterium, which is 1 here, right? So here the N, this is the I value, and we have the plus 1. So total here 2 multiplied 1 multiplied 1, which is again 2 plus 1. There will be a 3 signal in case of CdCl3. So that's the reason we get the 3 signal. So this is the formula. I just mess up the position of the bracket. Hope this one is get clear, right?
Yes, sir.
Because the I value is different for this one, right? So that's why to put the value 1 in case of the deuterium. In case of deuterium, put and also as I mentioned, we take the 13C as a 1H decoupled. So that's why coupling due to the proton is get vanished, but coupling due to deuterium remain as it is. So that's why in the NMR spectra, we observe the for the CDCl3, we observe there will be a triplet in the CDCl3 NMR spectra. So this is the carbon, sorry, in the 13C NMR spectra. So this is the 13C NMR spectra of one of the compound, and and you can look here. There will be a signal due to the CDCl3 presented in from the solvent, right? So hope this one get clear now. And also also we have seen the standard for this one. So the tetramethylsilane is used as a standard for if you look at the 1H NMR spectra here, I have the example of 1H as well as the 13C, so I can show that one. So here there will be this TMS as a standard we have used in the 1H NMR. Also in the 13 CNMA spectra here. You can look here. So there will be a, you can see the small signal. So I will just calibrate this whole with respect to the signal, and I will select this signal as a, and I will just standardize this the 0 and this 0 due to the TMS, right? So, and remaining signal will get automatically recalibrated with respect to that 0. So whatever the value here. So let's take the, I'll just do the peak picking by, so I will just put, select the peaks, the remaining peaks. So these are the peaks presented here, right? In the carbon NMR. So this delta value is with respect to the TMS. So that's why we use the standard as a TMS in the proton 13C. And what is the question in the question given? So in the question, the TMS standard is used as for the 1H, right? For the 13C is also right. And for silicon spectra also we use the this TMS as a standard. So for the option, the fourth option is the correct here. Correct. Is anyone have a doubt up to here? All right. So the next question is, in the 1H NMR spectra of a molecule, the total number of peaks that we need to mention as well as the multiplicity observed. So let's take the one by one example. This is the A molecule and this is the B molecule. So let's take for the first molecule. So number of peaks observed. So here there will be one set of protons, another set of proton, here also another set of protons. So there will be a three peaks available, right? And multiplicity pattern for these peaks. So here don't get confused between the peaks and the multiplicity. So let's for example, as I have shown earlier, for one of the molecule, this molecule, right? So let's so for this proton, so for this proton there will be one peak, but if you look at the multiplicity, there will be a, it will be a doublet. So there we will get the two similar such signals in the 1H NMR as I shown earlier. But here, what the question says, the total number of peaks. So one, two, three. So there will be a three peaks for this this compound A. And if you look at the multiplicity for this one, so as I have shown earlier, the 2 Ni plus 1. But use this formula and calculate the how many number of peaks will be observed for this the first, second, and the third set of protons. So if you go one by one, so let's take this methyl group. And for this methyl group, it coupled with this CH2. There are two hydrogens. So it will be 2 multiplied by the N is 2, right? And I for the hydrogen is 1 by 2. And again, here it will be a plus 1, right? So if you just calculate this one, this will it will be a 2 plus 1 is equal to 3. So there will be a triplet for this methyl. Similarly, for if you calculate for this CH2, for this CH2, right? So this CH2 has the neighbor CH3. So that is total N is equal to 3. So if you calculate the same formula 2Ni plus 1, this formula, so it will be 2 multiplied by number of hydrogens here. It will be 3 hydrogens, and I value for this proton, it is 1 by 2, and again it will be a, so it will be 3 plus 1, there will be a 4, so it will be a quadrate, right? So these 3, it means it is triplet. So this first methyl shows the triplet, this CH2 show the quadrate. What about this CH2? So can anyone tell here? So for this CH2, if you look at neighbors, there will be a hydrogen, sorry, the oxygen here. and on the another side there will be a carbonyl group. So there are no neighbors. So this CH2 will show the singlet, right? So in this way you should able to solve the problem, right? Based on this topic. Also, in hurry, don't select the as it is answer from your assignment. I have changed some structure in here. So you should able to select the correct option based on the question given in the assignment. So let's take the another example, this example. So for this one, how many peaks are observed? The first question. And the second question, the multiplicity. Can anyone tell here? You should able to answer this one. So if you look at this, there will be a methyl group, sorry, CH3 and one CH2. And if you look at the this on the another side, there will be again similar groups are attached CH3 and these in between CH2. So I will just split the structure of this one. So this will be a structure like this, right? So this is the CH3 and another CH3. And if you look at this one, so it is a symmetric molecule. So we observe only the two peaks because of this methyl. The one is also the same methyl, and because of this CH2, there will be another second signal or the second peak due to this CH2. So we observe the number of peaks observed here too, and the multiplicity of this one. So this CH3 is coupled with the CH2, right? So CH2. So when you are calculating the multiplicity of this CH3, that time we need to take into consideration the n adjacent protons. So here, how many adjacent protons are there? N is equal to 2, right? So it should show the triplet as I saw earlier, right? You can use the same formula, 2n I plus 1, this formula. Put the value of n is equal to 2 and value of I, we know it is 1/2 for the protons, right? So you should able to get the answer for this one as well now. And I will show some another problem here. So let's take the some problem in more depth. So here we have here CH2, and you can also, let's take like this example. So in this molecule, so the question is, as you know, you can already able to solve how many number of signals here. So this will be 1, 2, 3. So we get the 4 signals, and multiplicity for this one will be the singlet, right? For this one, what will be the multiplicity? This couple with this. So it should show the triplet. Similarly, if you look at this one, so this coupled with this CH2, right? So it should show the triplet because there are only two adjacent hydrogens. Now the question is, what is the multiplicity of this CH2 group, which is I have highlighted here. So anyone here? So what is multiplicity of this one?
Sextet.
All right. 68 is the correct answer because here n is equal to this CH2, this 2 and this one 3, right? So total n is equal to 5. So by using this formula, so this will be 2 multiplied by 5 multiplied 1 by 2, and it will be plus 1. So total there will be a 6. So it will be a sextate, right? So this will be the show the sextate here. But if you look at, if you have some other example, here we have taken consideration the J values. J due to the, let's take this hydrogen as A and this hydrogen as a B. So J and this hydrogen, let's take as a star, right? So J H star H A is equal to J H star H B. At that time, it will show this 6 state as you mentioned here. But when they are not equal, at that time, the splitting due to the one is observed first, and then splitting due to the another is observed after that. So I have some example here. So I will just mention. So let's take the example of this molecule, which has the two different type of yeah, right. So let's take the example of this one. So we have CFH3. So at that time, and we are looking for the 13C spectra, the splitting in the for the carbon for this one. So what will be observed for this one here? So for this one, let's take the it will be a splitting. It will be the same as like proton. Generally, whatever we look for the by using this 2n I plus 1 formula, this formula will remain same. What happened here in this one for this carbon when you are looking for the when you are looking for the number of sorry splitting pattern of this carbon, so at that time, so there are two different type of couplings will be possible, like carbon fluorine coupling and carbon hydrogen coupling. These two different type of couplings are observed, and generally the JCF is quite higher than the JCH coupling. So at that time, what we need to take, so this the signal due to the uh, carbon 13, right? So this signal first, because of this fluorine, will get converted into the, if you put the value here, for I for the fluorine is also 1 by 2. So at that time, use the formula 2Ni plus 1. So it will show the doublet due to the this fluorine, right? So it will be a doublet, right? Because of the JCF coupling, right? And then we observe again the coupling due to the JCH. So because of there are three hydrogens, so it should show the quadrate due to the three hydrogens. So it will be a like this. Just draw it some symmetrical. I'll just draw with this one. And what is the oh, sorry, what is the intensity ratio? Can anyone tell me? So what is the intensity ratio of this quadrate? Quadrate. So this distance should be all distance should be the constant, right? So while drawing here, I have missed this one. I want to draw this perfectly, but you should know this distance between these two lines. All this distance should be constant. And also, what is the intensity ratio for this one? Can anyone? You can draw for this another one also. I'll just ignore. So what is the intensity ratio for this quadrate? According to Pascal's triangle. So this ratio should be 1:2, 3:2, 3:1. So these four lines should be in this ratio 1:2, 3:2, 3:1. Similarly, these four lines as well. So I'll just correct this my diagram. So in this manner, right? So it will show like this doublet of quadrate. So it will be a doublet of quadrate like this. The signal will be doublet of quadrate for this 13C. Understand now? Or do you need some more example in the same manner? So I'll just take some another same example, very similar. In this one, I will just take the for the protons only. For 1H inverse spectra, let's take example of, we have the example of CD to CH, sorry, CD to H2. . 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2 right? And here we have in the condition we have given J. Uh, Initially, I have written correct. We have here CH2 and this carbon we are this CH2 we are considering, and we have CD2, and there will be some X group here. Also, there are some another Y group on this side, and now we have to only focus on this in between CH2. So, what will be the multiplicity of this CH2 in the highlighted in the bracket? Also, in the condition we have given J HD is greater than J HH. So, what is the question is multiplicity pattern of this CH2, the highlighted CH2, right? So, as I shown, we have to go step by step. First, the we have to take into consideration the whichever J value is higher. First, give the first show the splitting due to that. So we have the JHD is higher. So we should show this splitting first. So because of this 2 deuterium, the signal, what will be the signal? So if you calculate this, how many the signals will show? 2 multiplied by n is 2 multiplied 1, right? Plus 1. So it should show 2 multiplied 2 is 4 plus 1, right? So it should show 5. So there will be a pentate due to this CH2 CD2 coupling. This is just a hypothetical example. So in this one, we'll observe first. Display 5 lines due to this kind of coupling. I will just ignore the intensity as of now because it will be too much complicated if I just show the intensity. The diagram will not be. So intensity will be as like you can follow the Pascal triangle. So intensity by Pascal's triangle. So you just follow the Pascal triangle, and that will be the intensity for this intensity pattern for this one. So initially we get the pentate because of this CD2 coupling, and later we have the CH2. So it should show the triplet, right? So each line will split into the three lines. So we get the I'll just draw in the green. So like this way. So we get the pentate of triplet in this case. So understand here. So any doubt in this question? Here what we have did the first show the coupling due to the one, and next later we could show the coupling due to the another group. So in the same manner as we seen the prior example of this CfH3 molecule, right? So this is also the same example given in the assignment, and you just need to show the number of how many groups of the peaks present. So this will be 1, 2, 3, and 4. So there will be 4 peaks observed for this molecule. And what is the most probable multiplicity structure? So for this one, it will show because of the CH2, it will show the triplet. This shows the quadrat. This show the singlet, and this also show the singlet, right? Any doubt here? All right, if you don't have doubt, we'll move for the another question. So here the as I have mentioned earlier, so we have given the example of that we have already solved, I think. So we have given one question. I will just change some molecules here. Instead of CF H3, I will just CF to H3. I will just take this example. And here in the question it mentioned, so J coupling for the CF is higher than the J coupling of value for CH. So what is the pattern seen in the 13C? So as I mentioned, so whatever the coupling is higher, show the splitting due to that one. So here, because of we have the two fluorine atoms here, so because of two fluorine, we get the triplet, right? So with the intensity 1s2, 2s2, 1, right? Then later, because of sorry, it is 2. Then later, because of this hydrogens, we need to show the splitting. So again, this will be 1s in the ratio of 1s to 2s to 1. This also in the ratio of 1s to 3s to 1. So we get the triplet of triplet here, right? Does anyone have any doubt here? Similarly, the next question is the 13C spectra of the molecule contain CH3F group is recorded at natural abundance of the 13C. The analysis of spectrum gives. I should show the options here. I'll just pick up some options. So this is the question from the assignment, right? Right. So these are the options. So which option correct here? The option is so it will show the J coupling due to the CH and CF. Also, it should show the J coupling to the HH as well as FH. So we are recording the 13C NMR spectra. So we will not observe any coupling due to the JHH as well as the JHF because we are taking the 13C NMR spectra. So this coupling will not observe. Also, this coupling is here. This option is also wrong, and this option is also wrong. So the option A is the correct option here. We will observe here JCH coupling and JCF coupling. So this option A is the correct option here. And we'll take one more last question. So here the question is given. The spectral pattern of homonuclear or heteronuclear A2 X2 spin system. So let's take the example of this A2 X2 spin. Ignoring the coupling due to the naturally abundant 13C. In this case, what will be observed for this one? So for this one, we observe the two triplet, and also we observe one at each respective chemical shift value because we have the CH2 group as well as the 2F2 here in this one. So I think this is good enough for today. So anyone have any doubt regarding this, whatever we have solved problem here? All right, if you don't have any doubt, I'll just stop sharing here. See you in the next video.